Hi, this video is going to go through question 4 of the November test. So 4A starts with a reaction where we've got iron oxide reacting with carbon to form iron and carbon monoxide. So FeO4 3O4 solid plus 4 carbon solid goes to 3Fe solid plus carbon monoxide gas. So why is this heterogeneous? Because we've got both solid and gaseous, especially in our product, solid and gaseous, both solid in our thing, but we've got the products and reactants are in different states. In part 2, so writing the expression for Kp for this, Kp is going to equal the partial pressure of carbon monoxide to the power 4. Now we needed rounded brackets here because this is a partial pressure. Fe3O4 solid, carbon solid and iron solid, so they won't go into an expression to work out the Kp. In part B, we've got then a question in terms of Le Chatelier's principle. Sorry, mispronunciation. The conditions of pressure and temperature for a maximum yield for the equilibrium shown above. So what would we have? So we've got CH4 gaseous plus H2O gaseous goes to 3H2 gaseous plus carbon monoxide gaseous. So the first thing we need to say is that our conditions, if we want to get maximum yield, is that we want low pressure and high temperature. I realise suddenly I haven't put the enthalpy data on. So enthalpy for the forward reaction here equals plus 210 kilojoules per mole. So we want, first of all, low temperature, low pressure, high temperature. If you said that, you got a mark. So let's go through the pressure. The right hand side has more moles of gas. Four on the right hand side, only 2 on the left. So if we have low pressure, the Chatelier's principle is going to work against that, and it's going to shift to the right and produce more of the gaseous compound on the right hand side. So if you've mentioned either the right hand side has more moles of gas or more gaseous molecules, if you said left hand side has fewer gaseous moles or gaseous molecules, you got a mark. So that was the pressure. The temperature, forward reaction is endothermic. Got you the mark. So if you have high temperature, this is the reaction is going to work, or the equilibrium is going to work against that and try and lower the temperature, so shift to the endothermic side. Just ask why operational conditions might not meet this, and you could have 2 for these. If you use low pressure, so low pressure, you'll get a slow rate because we might not have as many frequent collisions as we like. If we have high temp, so you could have said either one of these, but they're both only worth, well, you can only get 1 mark for this section. So high temperature uses lots of fuel. They wouldn't have allowed expensive. So high temp uses a lot of fuel, a lot of energy. But if you said expensive, you wouldn't have got the mark there. So that was out of 4. Part C was a great question. And we start with the reaction N2 plus 3H2. I'm just giving myself plenty of space here. Goes to 2NH3. So the Haber process tells us that at the beginning, so initial, we have 0.8 moles of N2, 2.4 moles of the hydrogen, and there's 0 to NH3. And at equilibrium, there are 0.36 moles of 2NH3. So that has gone up, increased by 0.36. If we then work backwards and look at the nitrogen, this is a 1 to 2. So for every 2 moles of this formed, one of these is reacted. 1 mole of nitrogen is reacted. So we've got 0.36. So 0.18 must have reacted half of this nitrogen, and that gives us a new equilibrium mole value of 0.62. And this, for every 2 of these, we get 3 of these. So that must have been 0.54 moles of hydrogen used up, which gives us 1.86 as the new equilibrium number of moles here. So if you've got 0.62 and 1.86 here, they were worth a mark each. Then we need to work out their concentrations. Now this is in a total volume in the equilibrium mixture is 5 decimeters cubed, so we're going to divide each of them by 5 to work out their equilibrium concentrations, and that will give nitrogen at 0.124, hydrogen at 0.372, and ammonia at 0.072 moles per decimeter cubed. Again, all 3 of those worth 1 mark. So far, this sigma smart question, mark there, and then all of these for 1 mark. Next up is our expression then. For this, we'll have a concentration of ammonia squared over hydrogen cubed times concentration of nitrogen. Or you could have written this out that you'd have Kc equals 0.072 over 0.124 times 0.372 cubed. I have one of those for a mark. Then if you do the calculation here, you'll get a Kc equal to 0.812, and it does in the mark scheme. It doesn't often do this when it doesn't say, it doesn't say appropriate number of decimal places, but they were after 3 significant figures here. They give their values for nitrogen and hydrogen at the beginning as 0.800 and 2.400. So they're after at least 3 significant figures there. Most of their values they give to 3 significant figures previously. Then, so that gave you 0.812, and the units for this, so that should have been squared up there, missed that out, will be moles per decimeter cubed times moles per decimeter cubed divided by 4 lots of moles per decimeter cubed. So 2 of them cancel out, which gives us 1 over moles per decimeter cubed squared, and that will be moles to the minus 2 dm to the 6. Should have the positive integer first really, so it should be dm to the power 6 moles to the minus 2, but it'd accept that is your answer. D part 1 wanted the Kc for that expression. So the equation was 2SO2 plus O2 goes to 2SO3. So we'll have SO3 squared because 2 before it, times the concentration of SO2 squared times the concentration of O2. So that was 1 mark. The units here would be decimeters cubed per mole. Then in part 2, we need to determine the amount or the concentration of SO3. Well, no, equilibrium amount. And just saying this one, give you a final answer to an appropriate number of significant figures. So we have 0.0540, so 3 significant figures here, mole of SO2, and 0.027, again 3 significant figures of O2. So concentrations first, so we can put them into our expression, and we have this in 400 centimeters cubed. So that will be 0.4 decimeters cubed. Easiest way to do that is just to times each of these by 2.5 to work out how much is in a decimeter cubed. If there's 0.0540 in 400, then there'll be 0.135 moles per decimeter cubed, and there will be 0.0675 moles per decimeter cubed of the oxygen. So then we can go to our expression we worked out before. We can start to rearrange. We know Kc. Kc is 3.045 times 10 to the 4, and that is going to equal the concentration of SO3 squared over 0.135 squared times 0.0675. So rearrange all this times this side by this, and then take the square root, and you get equal to concentration of SO3 equal to 6.12. Now that's the concentration. This wants the amount in moles, so the equilibrium amount of the SO3. We then need to work out if that's in 1 decimeter cubed, how much will there be in 400 centimeters cubed. And to do that, I'm going to divide by 2.5, which gives you 2.45 moles to 3 significant figures. So that would be then your answer. And that is question 4.